So, welcome everyone, and thank you very much for being here today for attend this S34I webinar, in which we will have, of course, our coordinator from the University of Porto, the Professor Ana Teodoro, and some of our partners that will be showcasing their results within the S34I project. So, first of all, I would like to give the floor to our coordinator, Ana Teodoro.
So good morning. I don't know if you can hear me because I have some, yes? Okay. So good morning to all. My name is Ana Teodoro. I'm the coordinator of S34I project. S34I project is a Horizon project funded by European Union that is researching and innovating new data-driven methods to analyze Earth observation data, supporting systematic and continuous monitoring regarding the three different phases of the mine life cycle, so exploration, extraction, and closure and post-closure activities. And the main objective is to increase the European autonomy regarding raw materials resources and, of course, using Earth observation data and techniques. The S34I project is delighted to have your participation in this webinar that will show the work of IGME and the University of Salamanca. So thanks for the speakers and the work that are being developed under the scope of this project, with the collaboration of the GeoExplorer in Spain, and of course the support of University of Porto and the Iberian Sustainable Mining Cluster. Thank you, Alicia, and your institution to organize this webinar. This is an initiative of S34I project dissemination plan. And the main objective is to highlight the innovative methodology in mineral exploration that have been used and developed under the scope of S34I project. So thanks to the speakers, thanks to all the attenders, and of course, a nice webinar for all. Thank you.
Thank you very much, Anna. So according to the agenda that you all have in your screen, sharing in the screen, I give the floor to Mercedes Suarez, Professor of Geology at the University of Salamanca. Mercedes, you can start to share your screen and we are ready to go with you.
Okay, thank you, Alicia. Thank you all participants. But if you don't close your presentation, I can't present it now. Okay, thank you. Here it is. Okay, it's okay, isn't it? Yes. Well, we will talk about the spectroscopy for prospection, exploration, and exploitation of ore deposits. But focus on the spectroscopy in visible near infrared and shortwave infrared wavelength. And sorry, because I have a problem with my mic. And we will talk about the Aramo pilot site because it's one of the cases of study in the project S34I. Okay. In this talk, I will talk about, first of all, a short introduction to the project and the objective. In a second place, I will talk about the work that the team of the University of Salamanca has in this project that is related to determination and validation of the spectral signature for exploration of copper, cobalt, and nickel in the Aramo Plateau that is located in Asturias. And finally, as one of the main goals of our project is to develop new methods, I will talk of other examples in which we apply this methodology. In this case, are very preliminary data, but they offer other possibility different to the Aramo pilot. And okay, a short introduction to our project that, as our coordinator explained, is related to the research and innovation of looking for new methods to study data of Earth observation. And the characteristic of this project, the main characteristic from my view, is that the project covers full mine life cycle, because the project study exploration, extraction, closure, and post-closure phases in the life cycle of the mine. All of them with aim to increase the European knowledge and the autonomy on raw material resources, obviously. As we said, we explore and prototype new methods of analysis of AO, and because there are many data sets that are still exploited from different European space-based missions. And the project tries to have as added value to achieve or to contribute to the mining digital transformation toward its sustainability and security. In a mining green transformation, obviously thinking in a circular economy. And for that, the consortium is formed by 20 partners from 12 different countries that are here in the slide in green color. And our coordinator, Professora Ana Claudia Teodoro. And the consortium is very well balanced, because it has a 50-50 industrial and research profile, because there are mining stakeholders, technological consultant companies, large technological industry, 5 academia, among them my University of Salamanca, 2 mining clusters, research organization, and 3 national geological surveys. And the objective at the beginning of the project, we are now in the last months of the development of the project, are related with this idea to achieve new groups of data sets, and especially new methods and prototypes. And all of them with the final objective to achieve a set, or to perform a set of recommendations for better policies and guidelines for Earth observation uptake by the mining industry. This is the general flux diagram of the project. We are now, as I said, in the last month of development of the project. We are now in the phases of validation and constructing a road mapping that in the future has to be, or we want that it's useful for different stakeholders and political. Okay. Regarding to the pilot sites that we are studying, there are 6 different locations related to these different phases in the mining life cycle. We have 2 cases in the exploration phases. That is one in land exploration, another in that is for coastal exploration. 2 are in the northwest of the Iberian Peninsula. 1 pilot for the extraction phase, and 2 pilots for closure and post-closure that are located in Finland and Germany. We will see very shortly these different pilots. And first is the study of an ore deposit that is onshore, unconventional deposit. It's located in the northern of Spain, in Asturias, and it's a matter of an epithermal carbonate-hosted copper-cobalt nickel deposit that is related with carbonate, mainly what we will see later in the Aramo Plateau. And the second pilot, in this pilot, there are 4 main points that are related to the construction of the spectral library in which we are working, to be applied to hyperspectral data obtained with a flight that was developed in April 2024, And also this spectral library can be applied or should be applied for satellite data. And also we have data for a LiDAR flight that was in September in 2023. In the Ria de Vigo pilot is the pilot to choose for study shallow waters. In this case, Ria's visas, there are the good geological condition for the occurrence of critical raw mineralization in shallow waters, because there are primary mineral sources, the adequate watering environment and transportation, and there are studying the possible accumulation of minerals rich in titanium, tin, lithium, and other. Okay, all of them to be able to map these mineralizations vivid, and using obviously OE dataset. In this pilot, different steps here are related to the study of ground samples, but constructing a spectral library, and studying imagery that comes from hyperspectral, but is a challenge underwater hyperspectral, and also satellite data. The pilot in the extraction phase is located in Austria. Is a big open pit and also underground extraction site with these are exploited marble, mainly calcitic marble, but also dolomitic. And the main objective in this case is to study the stability and also the waste deposit and that. They use different kind of data that we can see here, photogrammetry and this kind of observation, because they try to have a continuous monitoring of ground instability, to have in real time ground instability maps, also mineral stockpile volume for estimation, and be able to improve volumetric maps of mining waste deposit. And finally, the pilots for closure and post-closure phases are mainly related in three cases with acid mine drainage, AMD. First of all, is located in Finland and corresponds to a group of miners, underground miners in this area that we can see here, in which appear mineralization of copper, cobalt, nickel, zinc, also with other elements associated. And it's important to point out that in this area, pH is around 2, and it's not a monetary size between the project, even with the condition that it did correspond in a protected area. And obviously it's very important to have the knowledge of this AMD in real time, and for that the colleagues studying this site have studied sampling water and rock and soils, also with data acquired by dawn, different field measures and laboratory analysis, and finally to try to obtain these maps in real time of acid mine drainage. The pilot in Germany is this area cover a big area, around 7,000 square kilometers, in which there are a lot of former active pits, remaining lakes and channels, and in all cases with the problem of significant values of AMD. And the same for this area. The kind of data are here from UAV spectral acquisition of data and data from satellite with the objective to obtain the AMD maps for this mining area. Okay, once that I introduce the project, let me to pass to the second objective, that is okay, to show a bit of the results, the methodology that we have followed mainly, and a bit on the results that the University of Salamanca has in this project. We worked in the Aramo Plateau, the first site that I saw before, in which we have all miners, very well-known all miners of copper, cobalt, and nickel. In this case, our participation is with the objective to build the spectral library and obtain the spectral signatures to be applied with the other data. For that, we worked with the main set of data. We have the spectral library in the range of wavelengths that we use, and as visible near infrared and shortwave infrared. We study the mineralogical composition of a group of samples and also the chemical composition of the samples. Chemical composition and the samples were provided by Aramo, that is a company, one of the partners of the other partner of the project. And the objective, as I said, is to elaborate the spectral signature for the geological materials that outcrops in the surface of Aramo Plateau. Well, the Aramo Plateau that is here is, as I said, mainly formed by limestone and scarce or not so abundant dolostone that are here in this map. The area, as people who know the Iberian Peninsula, is strongly affected by the formation that obviously influence in the mineralization. Okay, but we study this very wide group of samples in which we have samples that come on the surface of the outcropping rocks in the area, but also samples from soils, and a group of samples that come from the old mines in the region. With the samples that correspond to the surface of the plateau, we randomly select a group of samples that we study by conventional mineralogy by using X-ray diffraction. And with this data, we determine a group of mineralogical associations. Is to say, there is a big variability in the composition of the surface of the plateau with different minerals, calcite, dolomite, quartz, gypsite, malachite, etc. But this mineral appear in different mineralogical associations. The first work, therefore, is to classify the samples according to the mineralogy and determine and obtain this mineralogical association. Here we have several of them. For example, we have a very, very wide group of samples that are mainly formed by calcite with minor amounts or scarce amounts of other minerals. There are other group of samples in which dolomite is the main mineral with small amounts of calcite, and others in which these minerals are in different proportion but more or less similar. Other group in which calcite is the major mineral, but in this case with small amounts of clays. Okay, there are this group of mineralogical association for outcropping rocks that have here the first 5, 6, sorry. Calcite is always present. In some cases, is the major mineral in other cases is minotite. And also we have two groups in which there are no calcites or is not very important. First of is formed by quartz with goethite, and the last is formed mainly by giepsite. If we include, obviously, samples that correspond soils, we see in this case that the mineralogy is very similar. We have mainly phyllosilicates with quartz, and difference is the presence or absence of talc and giepsite. From the mineralogy, we differentiate these three mineralogical associations. Chloride or phyllosilicates are very complex in this area, and is a mixture of interstratified between chloride vermiculite with always illite present in different proportion. And once that we have the mineralogy with this proportion of the samples very well known, we obtain the spectra for all samples, almost 900 of spectra. I want to point here and reinforce later that one or the principal advantage of this methodology is that we can obtain this data in a very, very short time, because its spectra takes no more than 1 second. We invest more time changing sample, changing location at the field tip that acquiring the data. And once that you have full data, we can work with all packages together. We need at the same time to work with 100 of samples than 1,000, because it's in a group, okay? And we have the spectra for all samples, but the first step is to compare the spectra of the samples that we have studied from X-ray diffraction and realize that each group have this similar spectra, because as the mineralogy is the same, the spectra should be also the same or very similar, okay? And the steps will be, okay, we have the mineralogical association, we compare with the spectra and obtain the mineralogical, the spectral signatures, because the last or the main objective is to classify all samples according to this spectral signature. Okay, here there is one of these mineralogical association. I think that is calcite with malachite by the morphology of the spectra. And we realize how, in fact, all samples that correspond to this group have a similar morphology of the spectra. Therefore, we can obtain from them the spectral signature for this mineralogical association. How? By a very simple method, that is to obtain the average spectra of the group. Once that we realize that all spectra are similar, we obtain the average, and this average is the spectral signature for this precise mineralogical association. And for example, here we see the spectra for samples very rich in giepsite, that they have these characteristic absorption features, or the spectra for the mineralogical association, this spectral signature for the very rich in calcite group of samples, or for the samples that are rich in calcite and malachite. Obviously, in a first glance, the spectra are really similar, but if you realize there are small differences that are related with the presence of malachite in these samples. Or here, other very different that correspond to samples that are rich in goethite. In this case, the difference is located in the visible region of the spectra, because in most cases, the difference are in the shortwave region of the spectra. Okay, as I said, we obtained the spectral signature from the average of the spectra of the group. Here we have the spectral signature that we have obtained for this 11 mineralogical association, the spectra, and the spectral signature that correspond also to the second derivative of the spectra, because we can work not only with the first data that is the spectra, but with all kind of treatment of first and simplest is the second derivative of the continuum removal, that is to put in a same value of all spectra, or with different mathematical and statistics treatment of this spectra. Here we have the mineralogical association and the spectral signature. As we see here, we have 11 mineralogical association, but only 9 spectral signature, because it's not possible to distinguish these two groups, calcite, dolomite, dolomite, calcite, and the presence of talc in soils. It's for that we have at the end 9 mineralogical association, spectral signature. And now that when we have this spectral signature, we have to apply to all samples to be able, but this way, to know the mineralogy of all these hundreds of samples, and also to validate, because with this spectral signature, we can work in the remote data or with the remote data. First is the statistic treatment of all spectra. Here we have the spectra that correspond to outcropping rocks, more than 300 samples, and in a very big cluster diagram, in which we see different grouping. When we analyze this, each one of this group, we realize that in fact the cluster has each cluster has a similar morphology in the spectra, as we see here. In the middle we read the spectral signature, both for the spectra and for second derivative. This example corresponds exactly to the mineralogical association number 8, that is mainly formed by gibbsite, and it's occurred for all groups. The manner informed. Okay. Sorry. Okay. And here we see how this clustering is perfectly related to the mineralogical association. What this means? This means that if I choose one of these samples, for example, here in this group, each sample of this group should have quartz and goethite as main minerals, or in others here, for example, all this group of samples, each one of them had to be mainly calcite with small amounts of malachite. Is to say, we have the classification from the mineralogical point of view of all of samples, okay, without to perform other kind of mineralogical or geochemical analysis that need time and economical invest. But okay, we have the spectral signature, but we have to validate them. And for this, we use two ways. One is a statistic, in which we repeat this clustering analysis, but introducing the spectral signature, and obviously it matches very well. Each spectral signature appears in its group. And other way is the analysis of a newly randomly selected proportion of samples. In this case, it was 10% of each one of the clusters, okay? And we realize how the composition that we obtain by X-ray diffraction match with the composition that we predict from the spectral signature. From this data, we can say that from a group of samples, we obtain the spectral signatures. With these spectral signatures, we can know the mineralogy of all samples. And I want again to repeat, in a very, very short time, and without to perform other different kinds of analysis. The acquisition of a spectra takes a second, and we work together all data in the statistical program or in an Excel file, as we will see in the next examples. And by one way, we are able to study a very, very high number of samples in a quick manner, but also we can apply this spectral signature to the interpretation of the image obtained by different remote sensors, in our case, hyperspectral data from the flight and from satellites, because we can compare our spectral signature with the remote data and identify or classify the pixel according to the predicted mineralogy in this group of spectral signature. But okay, related to the mineralization, what is useful or not? When we compare geochemical and mineralogical data, we relate. We see that there are very high correlations among calcite, malachite, cobalt, copper, and nickel. Is a bit surprising in principle that is related more with calcite than to dolomite, but is related to the geology and it's not the objective today. But there is this strong correlation, and this means that as there is a relation among the different ores that we are interested in, and the minerals are related or are classified according to the spectral signature. This means that there are spectral signatures that are related to the element of economic interest. In this case, cobalt is clearly related with mineralogical spectral signature 1, 6, and 8. This means that when the hyperspectral data and data from satellite are studied, if we apply the spectral signature, we can know what pixels have more probabilities to have mineralization, or we can know what pixels have very few probabilities and have no more interest to focus new phases in the exploration and prospecting. In this case, we can say that the spectral signatures 1, 6, and 8 are related to the mineralization, and therefore the pixels that fit with these spectral signatures will be the space on the surface of Aramo Plateau with more economic interest. Okay, and finally, let me to show other cases, other examples of spectral signature in general for the knowledge of our deposit, in which we have used other ways to relate the question that we have to solve in this mine with data from this spectroscopy. Because a spectral signature can be applied to data acquired with different sensors. of course, portable sensors as we use our spectroradiometer is a portable equipment from ASD company, and but also this spectral signature can be applied to data obtained with different support, proximal or remote, for example, to know the mineralogy of cores, and to be able, as we see in this picture, the mineralogy in full section of a core, or by remote data obtained with plane or satellite, as I said. And for this, I saw other examples that we are now working in the group. One of them is the lithium deposit of Valdeflores. This deposit is located in the more or less center of the Iberian Peninsula toward the west, in the province of Cáceres, and is in this syncline. And the mineralization of lithium is mainly in micas, because lithium appears as an octahedral substitution in micas, and this implies that it's not easy to know the content of lithium in the micas. In principle, we thought that these lithium-rich micas should have a spectral signature, but when we study samples, we see how it is not possible to distinguish what micas have or no economic interest from the content of lithium, because the amount of lithium is very different. Here we have the correlation between amounts of lithium and potassium, because lithium is one of the octahedral cation in micas, and potassium is the interlayer cation. And the amount of potassium sorry, is related to the amount of micas, but not all is potassium and lithium is not directly correlated, because we have micas with very high amounts of potassium, is to say micas, sorry, that have very small amounts of lithium among the others. We classify the spectra according to the values in the shortwave infrared region in this group, and we relate the morphology of the spectra, is to say, in this case, the kind of spectral signature that we use in Aramo, a conventional spectral signature, because it's only related to the morphology of the spectra, to the position of peaks. And we see how there are several groups that contain the highest values of lithium, but in this group we have samples with very few amount of lithium, and in this other we have samples with a small amounts, but also samples with high amounts. If we use only the morphology of the spectra or the spectral signature, we are not able to classify very properly according to the lithium content, because it's related to the position in the structure of micas. And we try with different statistics treatment, and at the end we found this relation, these two specific values in the second derivative of the spectra have high correlation values with the content of, in lithium. And when we plot these two values, okay, here, and we plot all samples more than for spectra, I don't remember exactly the number, for 440, something like that. And we classify them according to the content in lithium in intervals. For example, res circle are between 2,000 and 3,000 ppm of lithium. We are able to classify samples with economic interest and without economic interest. in this graph. And we have to remember that once that we have the spectra, we put together in an Excel file this data, plot the data, and we have the classification. Here we have other examples. In this case, we try to use spectral data to quantify mineralogy in an exploitation of a deposit of a special clay that is located in Tamame de Sayago in Zamora, in Spain. In this deposit appear different proportion of two clay minerals with economic interest, but with very different properties that means that are for different industrial sectors. And it's important to classify at the quarry the materials, and the company at this place classify in 5 industrial products according to the proportion of these two minerals. And they use ordinary chemical analysis and sometimes diffraction, X-ray diffraction data to classify materials, and they classify on the pit as 1, 2, 3, 4, 5 type of materials to work and the material to the plant. But when we study the materials of the deposit, we obtain a regression model that allow us to calculate the content of smectite and the content of kaolinite from data of the intensity of several peaks in the second derivative curves of the spectra. When we compare semi-quantification of time by the two methods, by X-ray diffraction and by spectroradiometry, we realize that there is a very well agreement, but the difference is that we cannot have a very large number of data to be able to know in detail the quarry with spectroscopy, but when we have to perform chemical analysis of X-ray diffraction, we only take a very short number. We need more time, we need to spend money in analysis, and in this case, as I said, is achieved in only a few minutes, once that we have developed the spectral signature. And two very short examples to finish. One of them is this deposit of paleoskite, other industrial clay that is located in Maderuelo, in Segovia, also in Spain. In this case, paleoskite appear with these other minerals, and for quantification here, we have obtained this equation, again, with the intensity of 1 peak in second derivative curves. And lastly, also we quantify smectites for Miraflores basalt. Smectites are secondary minerals in this basalt, but they have a very high, strong impact in the cost of the construction of the third set of locks of the Panama Canal. The overruns were in billions. And the quantification of a very, very large number of samples was achieved by this method. In this case, is a regression straight as we see here that allow quantify more than 466 spectra that correspond to different cores, and know in detail the presence of smectites in the area. Again, in a very short time, 2.5 days to acquire the spectra, a few moments to obtain the number, but obviously a time to obtain the spectral signatures. That we do in our group is to develop the spectral signatures to try to solve different problems in mines. And is that we said? Okay. We go a bit more than conventional spectral signature. We look for other MINES spectral signature as this graph, equation, and that. And with this, I finish. Thank you for your attention. Here we have web place for the project. At that moment, obviously, there are a lot of data that are not open still, but there are a lot of data that are accessible here in Senado. The contact of the coordinator and project manager and my own contact here by email. And thank you again, and that is.
Thank you very much, Mercedes. It was so insightful to hear you and to hear also the developments that you carry on within the project. So we put the chat, but you have also the floor available if you want to elevate some comments or questions to this first part of the webinar. I can see that we have one in the chat. I'm gonna read it. What are the main challenges in validating a spectral signature for these minerals in exploration, Mercedes? Because maybe I think you were talking about the rapidity, the short lead time that you get when you are using this kind of technologies, but which challenges did you face?
The challenge is to be able to find the spectral signature that solve the problem. This is the challenge, because in its case it's different. I saw here different examples. In one case is projection in a binary plot with two data second derivative. In other case is the equation, that regression equation. And in the case of Aramo, it was the simplest way, that is the conventional spectral signature obtained at the average of a group of similar samples. This is the more conventional way to obtain a spectral signature. In fact, when we are talking in remote sensing data in general on spectral signature, we refer to the morphology of a spectra that is related to a certain composition. But in our group, we use the term spectral signature in other way, because we apply to different problems in mine, in exploitation and exploration of mines. And the challenge is to be able to develop the spectral signature. And for people working in mineralogy, it's very good challenge. Interesting.
Thank you very much, Mercedes. I don't know if anyone has any questions or thoughts to share with the attendees. I can give you 1 minute to think about it, or maybe we can address this at the end of the webinar after the session. Yeah.
Because
okay,
we consume the time of the colleagues, and at the end
we are perfectly on time, Mercedes.
Thank
You were super precise. So I'm going to give the floor to the Instituto Geológico Minero de España with Javier González, and also to Antonio Ruiz in collaboration with the IGME in the samples that in the test that they were working on in the pilot of Vigo, in the area of the beach of Vigo in Galicia, Spain. So Javier, the floor is yours.
Thank you, Alicia. Can you hear me?
Yes, perfectly.
Yes.
You can also share your screen if you want.
Yes, thank you. Thank you very much for this invitation to present today. I would like to introduce Antonio Ruiz, manager from GeoExplorer. We are investigating an area, is the Ria de Vigo, that is, as previously Mercedes was presenting, is the pilot site in the shallow waters and coastal area. I will share with you my screen right now. Wait a moment, please. Oh, sorry. I have a problem with my presentation, but wait a moment.
It's okay. Take your time. In the meanwhile, if you want also, we can address the questions for Mercedes
Yes.
that some of the attendees put on the chat. The first one is Luis, that is asking, could you apply this methodology to hyperspectral satellite, for example, Prisma?
Yes, I was started reading this question. Of course, as I said, spectral signature can be applied, not only can be, should be applied to the interpretation of the images when we try to analyze this data in terms of mineralogical composition, because it's not possible to compare exactly or directly from spectral libraries, because the spectral libraries contain very good data, sometimes match very well, but when we have a mixture of minerals, we don't have the proportional mixture of the spectra, because, for example, in our group, we study different cases of artificial mixture of minerals, and we realize that some minerals are have a very small signal with this technique, another very high. And if we compare two pure spectra with your samples, you can be very or have very strong mistake. But obviously, it's possible to apply the spectral signature when you have the mineralogical knowledge of this material. We apply after to this kind of data, this kind of prisma or other images, and we can have the interpretation of mineralogy. In our project, our colleague developed this work, and they have at this moment finishing the mapping of the mineralogical composition of the Aramo Plateau with this, using this data. Okay.
Thank you very much, Mercedes. I don't know if Javier, are you ready
Yes.
or we?
Yes.
Okay,
Yes,
so
we are
Christophe,
ready.
I apologize. We will back to you after this session. Okay, thank you.
Is sharing the screen right now? Okay. On this image, you can see one beach in the north of Spain, in Vigo, and the surface is covered by these kind of minerals in black or red color. And we are exploring critical raw materials in the connection between land and sea. This area is now with us the white area, because it's not very well reflected or in the cartographies and for metallurgy or also for geology. And therefore, it's so interesting to explore the connection land-sea to explore minerals with new technologies, air observation technologies, and others. No, in this case, you can see our part of our work in north of Spain, but in the surface we can distinguish the places, but we now to see what is occurring under the surface beneath our feet. We need to explore or understand how is the distribution, the geometry, the resource estimation under the surface, because we have on the surface titanium, niobium, tantalum, rare earths, and other elements. But how these deposits are distributed under the surface, or also how these deposits are distributed on the sea floor, on the surface of the sea floor, or below the sea floor. And therefore, we were contacting with a GeoExplorer to investigate the distribution with GeoRadar of these minerals, of these kind of deposits, placer deposits under the surface. And we will see in the talk, GeoExplorer talk, the research done in the area of Ria de Vigo to know better, to increase the knowledge of the subsea floor, the subsoil of these mineral deposits. So interesting for resource estimation, estimation of geometry of deposits, critical minerals distribution, and all the issues to solve with this new technology. Is that all from my side? Antonio, the floor is yours, and you can start whenever you want.
All right. Thanks, everyone. Here's in Madrid. I mean, So let me introduce myself. I'm Antonio Ruiz. I'm from Geoexplorer. I'm a GPR, I may say, survived around 18 years ago. Before this time, I was working in civil engineering application. And about 2-3 years ago, I was introducing this technique, this methodology into mineralogical survival. So let me please to show here. Compartir pantalla. Javier, can I ask you for upside?
Yes,
I can
I
also
will.
do it if you want, Javier and Antonio.
Yes,
Yeah.
if you can, it's better.
Oh, okay. No, but I mean to show the presentation. I thought compartir pantalla. All right, here. Excuse me. No, I mean.
If not, Alicia can share the screen.
I can do it if you want.
Yeah.
Please,
Yes.
please. Thank you.
Let me see. All right. Fantastic.
Wait, this one is the agenda. Sorry.
Exactly. Well, we will try to focus. I mean, excuse me, but I'm on with the video. I'm on with the micro, but I can't see where is my.
I'm already sharing your presentation, Antonio.
All
Can you
right.
see my
Okay.
screen? It's okay?
Perfect. It's okay.
Nice.
Perfectly see there. So this presentation have 3 parts, right? The first part, it's about methodology and about the history of the TAM. TAM is the name of use for this kind of filtering. All right, it's not something. The new here is to make a special filtering to separate between different materials. It's the first time here in geophysical records that we can differentiate between a material and another material. So, and in this first part, I will explain something about the history and about the capabilities we can do, right? The second part, as you can see, is this case, right? This survey in Playa de Vigo, in Santa Marta, and Playa del Bao, right? And the third part, you can see below, is the results, the geophysical validation, and the main implication, good main implication for the mineral exploration. So you can see the last one, please. Perfect. Here in the upside, right, how they work is in the upside, we can see that I explained that it's the latest explained was before that I was working there many years in civil application engineering and now use it in mineral prospecting. Mineral prospecting, why? Because when we started with concrete structure, so with bars inside, that with metal bars inside. So we elaborate sieving, filter sieving to just see where is the color change. Just see where is the bar. So how we just start is in study. How we start, how we do working is a normal georadar record, right? Georadar record, sorry. Then we make a normal filtering is the upside figure you can see, right? And then we apply this specific combination of filtering. So at the end of the presentation, in the geophysical validation, we can see the program is we use to do this sieving, this filtering, right? So in the upside part, you can see your common georadar, right? But in the downside, you can see the whole radiogram in gray, but the bars in blue, right? In this case, it's a very difficult case because it's two similar, well, it's not similar materials, but it's difficult to look at to precise exactly how much side it have the parts, right? So this is the beginning, and the beginning was civil application for palace, foundation, and many things, no? So I want to apply this in mineralogical survey. Next one, please. Then I'm gonna talk about the capabilities of we can do with this technique, right? And I mean into two types of capabilities, right? Here, the most important capabilities is to show that we can differentiate between different materials, we said before, and here we have we have something examples, right? We make a different using density, as you can see upside. We need to see a difference in density, in material, in metal content, electromagnetic content, also in crystallographic disposition with the same chemistry. We can differentiate between different crystallography certification and emission. So one of them, we can see some of them. Next one, please. There are five types of samples I'm gonna do. So one of them, all of them was civil. Most of them was civil application, and all of them are differentiated by what we use to differentiate. In one cases, it's the density. In other cases, it's density plus on other things. You know. In this, please, next one, please. Perfect. The other capabilities I was talking about is the physical capabilities, right? This is a georadar survey, and then they have many new ways to explore. I mean, for instance, some people here is listening talk about ask us about very complex topography, and I want to say from here that for very complex topography, they can use two things. You can see here by drone, right? But also the upside picture left one is a kind of antenna. It's like a long wire, right? That you can move on the rocks, and you can move all the complex topography. If it was not enough, we can use this same wire, take it with drones, and make an airborne survive anywhere. And other big capability have the GPR survive is there in the borehole, using the borehole antennas. Many of them ask as well for how much deep we can see, right? Then we see that we have no limits because we can use borehole antennas until more than 2,000 meters. So it is not about how much from the borehole, how long. So it depends on the type of antenna. Normally, it will be at maximum about 50, 100 meters. But nowadays in Africa, in gold explorations, some people is using a very special GPS survey, and then it's getting in about 250 meters in gold searches. So we can apply this kind of survey from many places. Also, in this presentation, we're going to show some submarine prospections, because we use the GPR on a boat, and we was exploring the submarine subsoil, and we penetrate into the submarine subsoil with very high detail that anyone has as well. So the next one, please. Right. Another thing I want to point out here is that the GPR covers the gap there is in the many geophysical survive between the direct recognition with a sample, with a borehole, with anyone, and the results you get with another geophysical techniques that you get at much better about 5 meters, 10 meters. I mean the ore body geometry. So there is a gap, right now gap between the sample, you can see with millimetrical if you want, or under, and the other technique. The GPR cover this gap because you can see from millimeter until ore bodies for 5, 10 or more meters. So there is where is the detail of many of ore bodies. The ore bodies geometry, I mean, not all the ore bodies shown. I mean, what is it really? What is the method? What is the material we're working for? And the GPR that cover that gap that anyone can get. So last one, please. Right, here is the same example of the beginning, right? We can see, say, a normal georadar survive, where the position part, right? And in step A and step B, downside, we can see the blue ones are the bars. In this case, we use many metal content and density for the distinguish. Next one, please. Here is an example of concrete covering for a tunnel. Maybe this is the most complex example we did before, because there is only separated in gray. Sorry, is the tunnel with the covering, all right, and in brown tones are the land. So with this, with many precision. In the left part, we can see the trace land, how it's separated from the vertical line, and it means there is still concrete. Next one, please. Next one, please. Right. Here, there is no covering of the tunnel, and the land is topping directly over the tunnel ring, and there is no covering. We can see the brown part near the 20 centimeters of the ring. Next one, please. Next one, please. Right.
Sorry, Antonio, it takes a little bit in between. I push the button and the image appears in your screen. Sorry.
Then you get it out. Sure, probably will be more time. So now we are turning. This is another example. Here is an exocard. You saw it upside. It's an exocard fracture. Inside is a calcita. Excuse me, I'm saying in English. Calcite, and the rest is the same limestone. So right, this is the case. Another case. This is simply here because we can differentiate that level with the mineral concentration used in the whole deep, because it's the same chemistry. Here we can differentiate. We will differentiate using the crystallography distribution. Next one, please. This is the normal radiogram, right? We can see not with clearly, but clearly the line, upside line, right? This is the fracture. Downside the same picture from the fracture, right? And inside the fracture is a clay and this calcite, right? It's not only clay. It's not only calcite in the fracture. There's also clay. So next one, please. Here in the trace, this blue line we can see is like anyone we can see, and it's very particularly differentiated the plane. So now we're going to use the TN process filtering. Next one, please. And all the limestone is nearly just in yellow tone, and in the fracture that I can do from here soon, but well, I will distribute for everyone this presentation, and you can check that in the all the fraction there are parts that are gray, and there are parts that are brown, and there are parts are red. The red ones that fill not fill all the fracture is like a normal. There's a normal, not fill the fracture, but what is red, the part is you can see as red ones, there is calcite, crystallographic calcite, with the same chemistry upside and downside. Next one, please. All right, here we have another civil example. Here in the middle, this is the monitor of the georadar directly, and we can see in the middle a vertical element about less than 1 meter, about 15 meters depth, right? This is nearly the most similar. Nowadays we have to a phyllon, right? But now we are going to applicate as well the TEM, right, to just see the phyllon. In this case, the wall foundation, right? Next one, please. Right, the other side is in red and similar colors because there is a mixture. It's a mixture with some concrete, right? But we can see the in gray, right, the wall, and in blue the rest of material. This is the magical of we get. Just see what you want to see as prospector, not just see many things that maybe you can see that probably no. You see here just what you've seen. In this case, the wall foundation, and in the case of we did in Vigo, sorry, heavy mineral layers, right? Next one, please. This here is not applied the TEM filtering processing, but is filtered like is here because it's similar for us like to ice-scar mineralization or something hydrothermal as well, or metamorphic contact. In this case, it's just an alteration, degradation as well, because in between the soil and the limestone perfectly, and we can see all the degradation, and in the downside we can see as well the voids because it's karstic, and we can see in red the cyanide the holes, but this will be very similar to one scar, to an hydrothermal, or something like that. The last before was similar to a phyllon. This was similar to a scar, hydrothermal, or something like that. Next one, please. This is something similar, but I want to skate how we can differentiate, for instance, in the left part upside, the voids, filled or not filled, no? Right? Next one, please. And talking about the capabilities, we have this, was we talking before, was about the mineralogical capabilities, because we are seeing most probably the most complex example that was in the tunneling I was showing you, because it's nearly the same density between the soil and the concrete. One then is 2.5 and the other one is 2.8, something like that. So the mini capabilities are great because we already demonstrated but that we can differentiate by density very closer densities. And if we use plus magnetic contact, metal contact, different crystallography, and so on, we can make a better sieving, right? And another capability was talking about here. I developed the borehole antennas because I think that here, not in Europe, in the north of Europe, it's very usual, but not here in this part, is really used the borehole antennas and this kind of protection. They have 4 points here to develop. Then is we can make with 2D sections, right? We can do a 3D composition around the borehole in about 50, 100 meters, but with the whole detail, right? In the left part, we see the mountain with a blank, with a white expression. That I mean that we can explore the range is decided. For instance, between 100, for instance, 400 until 1000, right? We can make continue scanning down the borehole and make it with some section to this section to recover a 3D section. Next one, please. Next one, please. Right. Here, this diagram is not mine. I was there when was taken. This is in Sweden, but it's not mine. It's a simple, very simple radiogram. But we can see it's about 30 meters around the borehole, right? But we can see very clearly the fracture, and we can see which one of them are close, which one are filled, and how much is the fillet or the fracture. So this is what I was explaining before. For instance, you intercept these planes in the upside plane, another plane. In the red part, you can see in the middle of the borehole, right? You have the two interceptation, but this in 2D. But if we make around sections, several sections, at the end, we can elaborate the piece, the rock piece, or the fracture we're shading, right? Next one, please. All right, let me see. Reflection. Yeah. Could we make a zoom, please, in the upside?
Do you want me to move forward to the next slide?
All right, perfect. No, you can, exactly. It's nearly the most the same. But I mean that in the, I put this radiogram here because at the same way we can explore for inside the borehole, we can see as we said before 50 or 100 meters around the borehole. So we can make two kinds of explore here. If you have the phylon, the metal body you intercept, then we can make a scanning and see how much far away is the plane going on, or if not, is the part the part downside. If we can give a second chance to the boreholes if they not intercepted the meridional body, because not all the boreholes have a good interceptation. So if you don't have an manual interceptation, we can search from the borehole. So next one, please. Right. The other important capability I want to point out in this presentation is the submarine subsoil prospection. Here's one example we did there in Playa Santa Marta. And we not use the TM sieving, right? But this very high filtering, but not TM filtering. But we can see at least we can see three kinds of deposit. Upside sand deposit. I mean sand because we can see here the next one we can see the detail. We can see the paleo channels, right? About 1 meter, about 1 meter, half meter, 2 meter, less about that. The paleo channels that is characterized from sand deposit. Another deposit is characteristic with less paleo channels and very layering with we thought is more with less energy, right? And it's not clay, but just very not clay sand very fine, you know. And the basement, not the rock basement, we can see the classic hyperbolas. They make the round elements. So a round element make a hyperbola very characteristic. We can see in the downside. So here we can see the blocks, right, in the top part, and an intermediate part with low energy, an upside part about nearly 2 meters, all right, of sand deposit. This deposit we can see here is a standing deposit of the beach one. That's one of the objectives of this program. It was that area between the land and the sea. This is the beach and this is the coastal, right? Here is about less than 4 meters bathymetry. We can see that, and then the subsoil. This is subsoil prospection with very, very high detail. I know there are many. There's some people here listening. They listen here. Many interested in this. And please, let's see next one. So here, this assume of the upper part, we can see the paleo channel. The rounded is the rounded elements is painted by me, but the rest of the lines, right? You can see the paleo channels. They make that geometry, right? This rounded with the paleo channels. Next one, please. So this was the first part. I've been talking about the capabilities, manual capabilities, because we can differentiate between different minerals using density, crystallography, chemistry, metal content, magnetic content, and so many and so that kind of physical characteristic, no? And the technical survive are the same one technical capabilities for GPR. And the best ones I thought is the strength survive, no? The strength survive in the waters and the strength survive in the land. Now here is where we use this technique for side these levels, right? These heavy mineral layers. Next one, please. And this part 2 is differentiated as well in 2 parts. The first part is what we did in Playa del Bao, and the second part is what we did in Playa de Santa Marta. What we did in Playa del Bao was the first calibrations was according to the ACTM lawyers, right? Geophysical technical lawyers. And there we make the calibrated, we make all the estimation, we make all the previous work, right? Also, we compare how we compare the charges. We can reach with an antenna with high definition antenna, the high definition antenna introduce low, but with many precision, very low or low frequency, get really deep, but we lost in precision, right? So we did the first part in Playa del Bao, and we saw below, and then the second part was the real change of this program, is to validate, is to show that this technique is able to differentiate this kind of materials. And we are able to estimate the deposit, at least the part we investigate. So next one, please. Here is in Playa del Bao, right? It's like a classical investigation we did. In this part, we use, we say you use a 1.6 gigahertz antenna and another one of 500 gigahertz antenna. The two antenna we prove there. Next one, please. And here, sorry, is the most important radiograms, maybe in all the whole exploitation. The challenge here was that we have to get the same layers we saw here in gray, right? Is the same layers we can see in a picture of a soil cut or pit, depending on how you say, right? It was really changed. The same ones layer you see here are the same ones layer you can see at the soil cuts. In this case, upside case, it is soil cut, sorry, number 36, and the other one, and the downside, the number 32. Next one, please. Here we can see, as it scrolled below, sorry, there was a perfect match between the layers and the layer we can see in the picture at the same depth and with the same thickness. This is the most reveal of everything, with the same at the same depth with the same thickness. Now we can prospect here and say how much heavy minerals layers I have here. I can do the counting in the radiogram. So this is the most important value and the most important contrast. Is a perfect match between the radiogram and the soil cut. Next one, please. Here the other one. Here less layer than like the other ones, but better to prove that it works. This case was made with a 1.6 high definition antenna, right? And other one, as I explained before, was with 500 medium antenna. So we can see, next one, please. Well, well, we will see later how much we can see with one antenna and how much we will see with the other one. Here, let's take this picture and this radiogram, because an important thing that we show there, that was the because it will be white monad theta and other transparent or translucent minerals that we can see in a soil cut because it's similar to the other materials, to the other sand, but is also revealed in the radiogram, and we don't see that color in the soil cut. But if you zoom inside one layer of this transparent or translucent layer minerals, right? We see on the top and on the upside part and the downside part a very 2-3 millimeters of black one with a sandwich of about 1 centimeter, more than 1 centimeter, this white monazita, and on the top again another dark layer about 2-3 millimeters. So I can see I want to mean with this that the GPR don't distinguish if the color. You can see if if it's gray, red, black. You'll see by density and magnetic metal content. So the GPR can reveal layers that we can see with vision, and this is here, right? Next one, please. Here is another target we did in Playa del Bao. Here is a gap sedimentation, right? We can see the layers from backside, from down to upside. The first layer is signed about N4. We can see in several places, right? At the end, at the beginning. The next one is level N3, but the N3 don't cross around the old radiogram. And this means that the level N4 was at the same depth, but this part, the right part, was down. Then the level N3 was covering, and until ulterior posterior and event of N2 that cover from one side to the other side. So he can reveal that there is no only this palette channel. We can see of the left, at the right part is a palette channel that mean a gap of the basement. So we can do many geological interpretation when we can see the layers. Also, there is no time, but we can differentiate between how is the layers modeled by the wine and how is the layer modeled by the waves. There's quite difference. So next one, please. Here is what I was talking before. In Playa Santa Marta, in Playa del Bao as well, we were taking was the site target for an antenna and what's the site target for the other antenna, right? And differentiate one antenna, the left one is the high definition, high frequency, and the right one is the 500, let's say, medium frequency, right? In the high frequency, we can differentiate 5 levels, at least 6 down here, right? Are the same ones of the we can see in the picture, and in the other side, and with medium antenna, we don't differentiate one of them because the medium antenna can reconcile over 2 centimeters, right? And in the left part, the 1.6 antenna can differentiate over 8 millimeters. So there's the reason there's more levels identified in the left part. So in Santa Marta survey, we use the 500 intermediate frequency because it's just because it was much faster. Not just for that. So next one, please. And then we have already validated in Playa Santa Marta that we have a perfect match between the layers and the radiogram, and that we have an antenna that can differentiate touches over 6 millimeter layers, and the other antenna over 2 centimeters thickness layer. So now we have already done the calibration of the previous work. Now we're gonna do a really survive of real prospecting of the Playa Santa Marta. There we did two longs profile of 25 meters as one, covering 100 meters, and as well 1, 2, 3, 6, 7 cross sections to 12 meters length. We will show you the transverse and one of the longitudinal. The other one we are using as well to develop an AE procedure to cover between the beach and the sea, right? Connecting everyone. So next one, please. Here is just what we want to see, where everybody was expecting to see, is the layers in black and dark gray, and the rest of the deposit and the rest of material just in gray. So we can hear a very important paleochannels with that form, conical form, in the right part, and another ones, smaller ones, in other parts of the radar gun, right? This is 25 meters. We can see more, but this is 25 meters, right? It's very long, and we can see clearly all the layers. This is what I think as well. The Aramo prospector is searching. It's just see what you need and evaluate. No, just differentiate. This is the next step of the GPR survive, just to see what you want to see. Sorry for repeat about that, but it's what we read. Just see what you want to see. No, next one, please. In the whole cases, I repeat this again. The whole cases, this was a perfect match between the soil cut picture, the soil cut layers you can see here, and the soil cut and the layers, soil layers, show it in the radograms in the whole cases, right? I put 2 here, but it's the whole exploration, right? Next one, please. Here I saw the 7 transverse cross sections, and I said before, in all the cases, it's certificated in, well, I mean, at the beginning, at the end of the radiogram, it's a soil cut, right? Between soil cut and soil cut is a radiogram, right? Or soil cut, radiogram, soil cut, soil radiogram, and after that we can see an average size of directly of the white layers, because we can see the white ones. Next one, please. Here, here is the longitude. Okay, here you can see again another paleochannel. I want to point out that in this paleochannel, cross the beach from other different places was the actual paleochannel. This is a paleochannel now discovered. It's full of mineral, and it's not you can see this a paleochannel covered, right? Next one, please. We have here more examples. I mean, when I say before, we can differentiate between what kind of energy of geological process. Another one, for instance, in the upside, we can see that the layers and the picture as well can see that they make us like a S, right? The sigmoid, that sigmoid form that make an aeolic form, you know. And the downside, another part, you can see more linear. This is more usual for what's zone than the other one. Next one, please. Here, right here, is the 4 longitudinally, we can see at least 3, 4 layers, important layers. There are much more, but I mean that's layer. You can see the radiograms that continue. If we don't you care, because I will provide you this presentation for everyone, right? But you can check when I provide you. We can check the continuous. We can push. I collocate a radiogram beside the other one to see that connection very layers. This is important because delicate important because I wrote before that this kind of layers, they're not have a development more than 25 or 30 meters. And in this case, we have several layers like N2 and N3 that have a continue more than 50 meters, nearly 80 meters. I don't mean the entire 100 meters, but nearly. So we can prove here that this kind of layer deposits have a very, very large development, longitudinal development that is not only about 20 meters, 25 meters. Here, the same layer, because continue, excuse me, we have continued for more than 70, 50 meters. All right, next one, please. Sorry, excuse me. As well, and no, don't get it, okay. At the same case, at the end, at the beginning, sorry, and at the end of each radiogram, there is a soil cut, IGME, soil cut, where they took the samples and so on. They make their geochemical, geochemical working. So each radiogram is proved at the end and at the beginning, sorry, and at the end, and is completely an interformat between the soil cut and the layers over here. Next one, please. Perfectly. Here is it's another one detail. Sorry, it's another one detail about the palette channels. It's another palette channel detected where no one thought that it was there, and are particularly interesting because they concentrate really. Well, you can see normally the layers occupied about the 60 upper centimeters, 70 centimeters, but in this case of polychannels, we get into more than half meter, 1.5 meters, nearly 2, and it cross inside the blocks, right? Next one, please. Here again, I want to show you, I want to make special push information about this, that in the whole case, there's a perfect match between thickness and depth. Next one, please. There is another one. I can say more. Next one, please. Another one. And here, thank you. And here is just the result that someone of I think I will thank, especially thank from people from Galicia listening here now, because this is the result, the very important result of this exploration, of this prospection. The actual polychannel is shown in this picture. Sorry, is shown in gray, but also in brown is the 2 polychannels we discovered as well. And at the end of this amount, we did an amount, as explained later. We did a very quick amount. Is we average the depth of the layers and make a multiplication with the density. That's all, right? But we use the density 5.0. We know that there are minerals over 5 point, but we just use 5, density 5. With the density 5 of these kinds of heavy mineral layers, we result into more than 100. Well, the average side is about 14, 15 centimeters. If you multiply the 15 centimeters with the density, then we obtain the nearly 700, more than 700, 800 tons. It means is here exposed nearly 1 ton per square meter or volume meter, right? It's so much more. It's really amazing. So next one, please. Here is the rates we did using, as I said before, S35, using this size, average size. This size is a mix between all the layers. Is not full of heavy metal layers. It's about probably 60, 70%. But it's true as well that we leave some layers under to the size of 2 centimeters. So we compound about that 14 centimeters that we multiplied by 4. So we also, the layers we can recognize there don't stop in the place we study. So this layer, at least, we can see +2 over 2, the spectrum we did. So at the end, we were talking about nearly 2,000 tons of heavy mineral layers. 2,000 tons in these bits, but we know there is about 30 bits just in Galicia. So we were talking about nearly 50,000 tons of heavy mineral layers. That is really amount of money, layers, and minerals. And the submarine survey we did, we saw this same deposit, as we can see before, that at least we can complete over 3 this amount. Just one bit like Playa Santa Marta could offer the bits and the sea deposit, the coastal deposit, right? Probably more than 150,000 tons, right? I say, if we multiply over 3 or over 30 all the beaches in Galicia, we could provide perfectly Spanish demand in this kind of, I thought. Next one, please. So many people ask for, and maybe Javier can explain this before, but now they ask me what kind of heavy mineral layers. And nowadays, what is here exposed is that nowadays the ICME is doing the geochemical samples, the geochemical analysis, and so on. But we can say we can show here the surface analysis that nowadays are still on, and what kinds of the 4 principal minerals. They are garnet, ilmenite, zircon, and white monazite, right? And I said before, this bits deposit could enlarge at least over 3, using as well the coastal, right? Next one, please. Well, this is the last part. It's about talking about the results, and I want to point out this again, and it's put here, that one of the targets of this program was increase the raw material, the European raw materials and deposit reserves, and here with this investigation, we could enlarge this deposit. We can enlarge this amount of raw materials. I think that in a very good condition. So Another target that had this project is to push a new methodology. For instance, in this case, for the GPR, I want to point out that GPR is evaluated by the European by the ESA agency, European Astrological Agency, like an AO, because it's radar as well. So it's a type of or EO observation. And I really thanks to Ikme, Javier, and this program to have show and validate this geophysical technique here, boosting this kind of protection that is perfectly validated, and we expect to upscaling, exploring more beaches, at least this kind of deposit. Of course, many more protection, but we can say that here now this kind of protection for this kind of raw material is validated, and we can enlarge much more the raw material here in Korea. Next one, please. As there's 2 points about the geological validation. One of them is the geophysical software we use, right? It's a very useful component between us, the Rad Explorer, that they provide and deliver the georadar company. When I bought the georadar, they gave me that software, and it's the same georadar. Here you have the list of the filters you can manage in the Rad Explorer. Obviously, we can see which one of them we have combined for make this kind of sieving, right? But is a foundation in a software program already validated, you know. And the other is just about the software, and the other pillar to put this validation is the statistic, the full match statistic. There was 22 cases, full match statistics in the 22, and almost it's more than the 22 cases. It's 22 cases with several layers with indeterminate thickness appearing between 0 and 65 depth. So that combination make an nearly impossible afford to it match. It's nearly impossible to afford to it match statistics. Next one, please. And for last, I want to explain some of the implication of this technique, GPR technique, filtering progress. And I want to the first one. I want to say that is a new way, because GPR solution for other like me for civil application was done not for usually for mineral prospection, but here is really as validated that we can use this technique. And the second point, develop that at the third is that you can see as prospector as what you want to see. Maybe this is the most important differentiated challenge we got here is because there is many geophysical information, but no one can see that here you have the gold, or here you have the anyone, and how much you have, you know, or how much is the geometry of the ore body deposited. And this is really useful for any prospector. Just see what you want to see. And the mining, the other one is any type of material, no? So next one, please.
Antonio, sorry for interrupting you. I just want to point it out that we are running out of time. I know that you are almost finishing, but just to let you know, okay?
No,
Thank you.
this is the last one because I can point again that we can
Perfect.
differentiate of any kind of mineralite. We can explore anywhere, and we can give a second chance to the boreholes, just exploring from there, if was intercepted or not. Thank you very much.
Sorry for rushing you, Antonio. It wasn't
No,
my
okay.
intention, actually.
Just say that here is not still a website because now we're building a new website. I have because I turned down everything about my last services, and now I'm focusing on just mineralogy. And now that's the reason we are. I hope next week, we can see at least some images of the website. Thank you all. I know there's many mineral prospection, mineral companies, and I really thank that showed you this this validated kind of prospection. Thanks all.
Thank you very much, Antonio. It was really interesting to see the potential of the results that you find out in the beaches of Galicia, in Vigo specifically. Thank you very much, Antonio and Javier. I don't know if someone wants to point it out some questions or comments. I think that within the chat, the questions that were before for Mercedes were already solved, but maybe you have anything to ask or to share with Javier and with Antonio.
By my side, Sol. Just thank you.
Well, I would like actually to ask, or maybe to put a seat of debate, that what do you think that are the benefits for both of you? I mean, Mercedes and Igme and Antonio, the benefits of this kind of technologies to implement in a real business case in the mining sector, because someone we find that there is a gap in between the research phase and then the uptake in the real business, right? So which are your perspectives, your ideas, your thoughts about this?
If I can say something, yes, in my point of view, these technologies are so interesting for the prospection without no invasive technology. We are exploring critical raw materials without alteration of the terrain, of the seafloor, of the beaches, with very, very low influence of the human activity over the environment. Therefore, is more environmental friendly and sustainable and easy to manage in short time for to obtain very good results. You can see here Antonio was presenting this distribution and geometry of layers with heavy minerals along beaches, and we can calibrate or estimate the resources. And I think is new technologies for rapid exploration of critical raw materials.
Just point out the same as Javier is the fact that I forgot to say that this is a no-destructive technique. Exactly. This is a complete no-destructive technique. We don't touch anything. So this is an EO technique and no-destructive technique. This is important to say. That is quite really quite responsibility with the government. So, yeah. And for the mining companies, here I am saying that they can see what they are searching. They can see a phylum. They can see inside the phylum if there is metal or not. And I hope I can upscale this investigation in Galicia and in and the rest of European beaches, because there is many potential of the raw materials here in the beaches for covering ourselves and ends the depends of China. I think that there is too many raw materials in the beaches, many more in other places, but the difference I want to point out from here, that here is already, it's a pleasure deposit. It's already taken out from the mountain. There is so easy to transform it. No, and I think that we can approach that kind of materials and that kind of situation.
Thank you, Antonio. And Mercedes, what
Thank
about
you.
you? What about your perspective?
Okay, it's really easy to resume in 3 words that are non-expensive, rapid, and green. That is. And for companies, I think that is the best.
That's fantastic. And I think that both developments within the S34I projects are also a proof of it. So thank you very much, you three of you. And I will give the floor if our coordinator, Anna, wants to make some conclusions or just hope to see you again in the next webinar. Who
Yeah,
knows?
just say goodbye, and of course, thanks to the speakers. It was very, very interesting, this webinar. Thank you for your availability to present these fantastic results of our project. So thank you, and of course, thanks to all the attenders for being here with us for these 2 hours. Thank you very much. Have a nice day.
Yeah, thank you very much, all of you. Just one thing before we go, we will send you the link for the video recording as well as the presentation of our speakers. So don't worry if you want to come back to the content because it will be available for you, okay? Thank you very much and have a really nice week.
Thanks to
Thank
you.
you. Bye-bye.
Thank you. Bye.
Bye.